Electrochemistry is the study of generation of electricity from the energy released during spontaneous chemical reactions, and the use of electrical energy to carry out chemical reactions that do not proceed spontaneously. The study of electrochemistry helps us in creating new eco-friendly technologies because the reactions carried out electrochemically are energy efficient and less polluting. A large number of metals, such as sodium and magnesium, compounds like sodium hydroxide, gases like chlorine and fluorine, and many other chemical substances are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. In human beings, the communication between the cells and the transmission of signals through the cells to the brain and vice versa have electrochemical origins. An electrochemical cell is a device that is capable of either producing an electric current due to chemical action or of producing chemical action due to the passage of electricity. There are two basic types of electrochemical cells. They are voltaic or galvanic cells and electrolytic cells. In voltaic cells, the chemical energy of a spontaneous redox reaction is converted into electrical energy. Voltaic cells are also called galvanic cells. The electrical energy produced by such batteries can be put to useful work, powering our cell phones, radios, and other devices. In electrolytic cells, electrical energy is required to carry out a non-spontaneous chemical reaction. When you recharge your cell phone battery, you are actually running an electrolytic cell. We will be focusing on voltaic cells in this module. Before we discuss how voltaic cells work, let's review the basics. Oxidation occurs when one or more electrons are lost. As a result, the oxidation number of a species increases. Shown here is an oxidation half reaction. Silver metal can lose one electron to form a silver ion. Reduction is defined as the gain of electrons. Note that the oxidation number of a species decreases when reduction occurs. For example, when a zinc ion gains 2 electrons, zinc metal is produced. We talk about half reactions because they only describe half of what is happening. If one species loses electrons, then another species must gain electrons. Oxidation cannot occur without reduction, and reduction cannot occur without oxidation. In an electrochemical cell, both oxidation and reduction must occur. Having trouble remembering the definitions for oxidation and reduction? Just think of an oil rig. Oxidation is loss, reduction is gain. Which of these represent oxidation? Which represent reduction? Equation 1 is an oxidation half reaction. An electron is lost and the iron 2 ion becomes iron 3. Equation 2 is reduction. The aluminium ion gains 3 electrons to form aluminium metal, and the oxidation state of aluminium goes from +3 to 0. Equation 3 is a reduction equation. Electrons are gained. Equation 4 is oxidation. 2 electrons are lost. When building a voltaic cell, one often starts with a half cell. A half cell, or a redox couple, consists of a metal electrode immersed in an aqueous solution containing the metal ions. A copper half cell is illustrated here. 2 half cells must be connected to build a voltaic cell. The electrodes are connected by an external wire through a voltmeter and a switch. This, however, is not sufficient for the voltaic cell to run. A salt bridge connects the solutions. The salt bridge allows migration of ions between the half cells while preventing direct contact between the half cells. In this diagram, the salt bridge is a U-shaped tube containing an aqueous salt solution, such as potassium nitrate. In some voltaic cells, a porous frit is used, or both electrodes may be immersed in the same electrolyte solution. When the switch is closed, the circuit is complete, and electrons move through the external wire. The migration of electrons through the external wire creates a current that can be used to run a motor or some other electrical device. The electrode where oxidation occurs is called the anode, and the electrode where reduction occurs is called the cathode. To help you remember this, think of an ox and a red cat. Oxidation occurs at the anode. Reduction occurs at the cathode. Let's consider what is happening at the electrode-electrolyte interface. Metal ions from the solution have a tendency to deposit on the electrode, trying to leave the electrode positively charged. Simultaneously, metal atoms from the electrode have a tendency to go into the solution as cations, leaving the electrode negatively charged. These two processes are competing. Depending on which process has the stronger tendency, a charge separation results. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentrations of all the species involved in a half cell is unity, the electrode potential is known as standard electrode potential. As per IUPAC convention, standard reduction potentials are now considered as standard electrode potentials. As mentioned earlier, the anode is the electrode where oxidation occurs. The anode has a negative potential relative to the solution. By convention, the anode is considered the negative electrode in a voltaic cell. The cathode is the electrode where reduction occurs. The cathode has a positive potential relative to the solution. By convention, the cathode is considered the positive electrode in a voltaic cell. The voltaic cell we've been discussing is called the Daniell cell. The net ionic equation for the Daniell cell is given here. Zinc metal reacts with copper-2 ions to form zinc ions and copper metal. Since oxidation is a loss of electrons, the oxidation half reaction has zinc metal losing 2 electrons to form zinc ions. Reduction is a gain of electrons. So, the reduction half reaction has copper-2 ions gaining 2 electrons to form copper metal. We know that oxidation occurs at the anode. So, zinc must be the anode. Copper must be the cathode because reduction occurs at the cathode. Electrons travel through the external wire from the anode to the cathode. By convention, when drawing voltaic cells, the anode compartment is shown on the left and the cathode on the right. Generally, voltaic cells are represented using a shorthand notation instead of a diagram showing the half cells. In this notation, a galvanic cell is represented by putting a single vertical line between the metal and electrolyte solution, and putting a double vertical line between the two electrolytes connected by a salt bridge. Using this notation, a Daniell cell may be represented as shown here. Under this convention, the EMF of the cell is positive and is given by the potential of the half cell on the right-hand side minus the potential of the half cell on the left-hand side. That is, the EMF of the cell is equal to E right minus E left. Using this convention, the EMF of a Daniell cell may be calculated as shown. In an operating voltaic cell, electrons flow from the anode to the cathode. The current flows from the positive electrode, the cathode, to the negative electrode, the anode. This current flow takes place when the circuit is closed, because a potential difference exists between the two electrodes. The potential difference between the two electrodes is called the cell potential or the cell electromotive force, or EMF for short. Cell voltage is measured in volts. The potential of an individual half cell cannot be measured directly. We can only measure the difference in potential for two half cells. To simplify this, reduction potentials are measured relative to an arbitrary standard, called the standard hydrogen electrode. You will learn more about the measurement of electrode potential in the next module. You have learned in the previous module that the potential of an individual half cell cannot be measured. You can only measure the difference between two half cell potentials, which gives the EMF of the cell. If the potential of a half cell is arbitrarily chosen as the standard, then the potential of the other half cell with respect to the arbitrary standard can be determined. Arbitrarily, the standard hydrogen electrode is chosen as the standard reference electrode. The standard hydrogen electrode consists of a platinum electrode coated with powdered platinum inside a glass tube. The platinum electrode is dipped into a 1 molar solution of hydrogen ions, and pure hydrogen gas is bubbled in at 1 bar of pressure. The standard hydrogen electrode is designed to carry out the half reaction shown here. A hydrogen ion plus 1 electron produces half a mole of hydrogen gas. By convention, the potential of the standard hydrogen electrode is assumed as 0 volts. When all ion concentrations are 1 molar, reduction potentials are called standard reduction potentials or standard electrode potentials. The standard electrode potential of an unknown half cell is determined experimentally by combining it with the standard hydrogen electrode. The EMF of the resulting galvanic cell is determined using a voltmeter. As the potential of the standard hydrogen electrode is assumed as 0 volts, the measured EMF itself becomes the standard electrode potential of the given half cell. For example, the standard electrode potential of a zinc electrode is determined by combining it with the standard hydrogen electrode and then measuring the EMF. The EMF of the cell is calculated as the potential of the right electrode minus the potential of the left electrode. Therefore, the EMF of the cell is equal to 0.76 volts. Thus, the standard electrode potential of zinc is equal to minus 0.76 volts. The negative value of the standard electrode potential indicates that zinc can reduce the H+ ions. Similarly, the standard electrode potential of copper is calculated as shown here. The positive value of standard electrode potential indicates that cupric ions get reduced more easily than H+ ions. In other words, hydrogen ions cannot oxidize copper. Thus, copper does not dissolve in HCl. On the other hand, copper dissolves in nitric acid due to the oxidation of copper by nitrate ions. The values of standard electrode potentials of some electrodes are shown in the table here. If the value of E0 is greater than 0, then the reduced form of the species is more stable than hydrogen gas. If the value of E0 is less than 0, then hydrogen gas is more stable than the reduced form of the species. As can be seen from the table, fluorine, with the highest standard electrode potential value of plus 2.87 volts, shows the highest tendency to get reduced to fluoride ions. Hence, we can say that fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium ion, on the other hand, with the lowest electrode potential value of minus 3.05 volts, shows the least tendency to get reduced to lithium metal. Thus, lithium ion is the weakest oxidizing agent and lithium metal is the most powerful reducing agent in an aqueous solution. You can also see from the table that as the value of the standard potential increases, from the bottom to the top of the table, reactions show a greater tendency to undergo reduction. The strongest oxidizing agent are found at the top, while the strongest reducing agents are found at the bottom of the table. As the value of standard potential decreases, half reactions have a greater tendency to oxidize. The reactions in the table need to be flipped to write out the oxidation half reaction, and the sign for the electrode potential changes. That is, the standard oxidation potential is equal to minus standard reduction potential. Try to answer this question on your own before checking the answer. Which of these is the strongest oxidizing agent? The nitrate ion, elemental iodine, or the dichromate ion? Answer: the dichromate ion is the best oxidizing agent. As shown in the table, it has the most positive reduction potential. Sometimes, inert electrodes, such as platinum, gold, or graphite rods, are used in voltaic cells. Inert electrodes provide a surface for electron transfer to occur, but they don't participate in the reaction. If inert electrodes are used, then the electrodes do not change in size as the spontaneous reaction proceeds. The potential difference between the two electrodes gives the cell potential. For voltaic cells, the cell potential is always positive. To calculate the EMF of the cell, add the potential for the cathode half reaction and the potential for the anode half reaction. The electrode with the positive reduction potential acts as the cathode, while the electrode with a negative reduction potential acts as the anode with respect to the standard hydrogen electrode. We'll develop our skills by completing a practice problem. Consider this situation. A student constructs a voltaic cell by connecting a half cell containing silver wire immersed in 1 silver nitrate and a half cell made from aluminium wire immersed in 1 aluminium nitrate. Identify the anode and the cathode in the cell. Write the balanced net ionic equation that occurs. Calculate the EMF of the cell. Identify the direction of electron flow in the circuit. Identify the direction of ion movement through the salt bridge. Which electrode will get larger? Which electrode will get smaller? There's a lot to do here, so we'll work through the problem one piece at a time. Let's start by consulting our table of standard reduction potentials. The silver half reaction has a higher standard reduction potential than the aluminium half reaction. This means that silver has a greater tendency to undergo reduction than aluminium. Since silver has the higher standard potential, silver will undergo reduction. Aluminium has a greater tendency to oxidize, so we will need to write an oxidation half reaction for aluminium. Since reduction occurs at the cathode, silver will be the cathode in this voltaic cell. Aluminium must be the anode, since oxidation occurs at the anode. Now that we've identified the anode and the cathode, writing the half reactions is easy. At the cathode, a silver ion gains 1 electron to form silver metal. The value for the standard reduction is plus 0.80 volts. At the anode, aluminium metal loses 3 electrons to form an aluminium ion. Compared to the standard reduction potential table, we have flipped the reaction. Notice also that the sign of the electrode potential changes as well when we write the oxidation half reaction. We need to balance these half reactions to show the conservation of change as well as mass. To do this, we must make sure that the number of electrons lost equal the number of electrons gained. In this problem, we need to multiply the cathode half reaction by 3. However, reduction potentials are intensive properties. Note that the value of E0 for the reduction half reaction is unaffected. Now, we are ready to find the overall balanced equation and calculate the cell potential. Adding up the two half reactions gives the net equation. 3 moles silver ions react with a mole of aluminium metal to form a mole of aluminium ions and 3 moles of silver metal. To calculate the cell potential, just add the cathode and anode potentials. We get E cell is equal to plus 2.46 volt. We have enough information now to draw a diagram of our voltaic cell. Electrons will flow through the external wire from the aluminium strip, the anode, to the cathode, silver. When the switch is closed, anions will flow from the salt bridge into the anode compartment, and cations will flow into the cathode compartment. As the cell runs, the aluminium electrode will get smaller, and the aluminium ion concentration will increase in the anode compartment. The silver electrode will get larger, while the silver ion concentration in the cathode compartment will decrease. Consider a voltaic cell, such as the Daniell cell we studied earlier. If an external opposite potential that is less than the cell potential is applied, the reaction will continue in the forward direction. If instead an external opposite potential is applied that is equal to the cell potential, the reaction stops altogether. There will be no current flow. If the external opposite potential is larger than the cell potential, the cell will now run as an electrolytic cell. The reverse reaction will occur. Electrochemical cells have a variety of uses. For example, pH meters use electrochemical cells. Electrochemical cells can also be used to measure solubility product constants and other types of equilibrium constants. They are also useful in potentiometric titrations. Standard electrode potentials are determined at 1 m concentrations. However, cell potentials are concentration dependent. How can we determine the cell potential if the concentrations are not 1 m? Walter Nernst was a German physical chemist who won the Nobel Prize in 1920. One area of his research was the concentration dependence of galvanic cells. The Nernst equation shown here allows us to calculate cell potential at non-standard conditions. E cell is the cell potential at non-standard conditions. E naught is the cell potential at standard conditions. R is the universal gas constant and T is the temperature in Kelvin. Also, N is the number of electrons transferred in the equation and F is Faraday's constant, 96,487 coulombs per mole. Q is the reaction quotient, or the ratio of products to reactants in terms of their molar concentrations. To calculate Q, the products are put in the numerator and the reactants are in the denominator. Raise each species to a power equal to its coefficient in the balanced equation. Molarities are used for concentrations as indicated by the square brackets. Remember that concentrations of pure solids and liquids are taken as unity. By converting natural logarithm into base 10 log and substituting the value of R, F and T equal to 298, the equation can be reduced as shown here. Let's work through a typical problem involving the Nernst equation. What is the cell voltage of a Daniell cell running with 0.1 molar zinc sulfate and 0.5 molar copper 2 sulfate at 25 degrees Celsius? The balanced net ionic equation is given here. Here's a strategy for solving the problem. First, you need to find E cell at standard conditions using our table of standard electrode potentials. Then, use the Nernst equation. From the half reactions, we see that 2 electrons are transferred in the overall reaction. Therefore, N equals 2. Now, we need to find E naught cell by using the equation shown here. E naught R is the electrode standard potential of a right-handed or reductive electrode, and E naught L is the left-handed or oxidative electrode. Now work out the expression of Q, the reaction quotient. Since the concentrations of solids are taken as unity, the reaction quotient Q becomes the concentration of zinc 2 ions over the concentration of copper 2 ions. Then, we can substitute our expression for Q in the Nernst equation as shown here. From here, we can substitute our values for E naught, N, and the ion concentrations into the Nernst equation. The ratio for Q can be simplified as 0.1 divided by 0.5 equals 0.2. Now, it's a matter of simplification of the expression E cell is equal to 1.12 volts. pH meters also work on the principle of the Nernst equation. Here is a typical problem you might encounter. A hydrogen electrode is in contact with the solution with a pH of 9. What is the potential of the electrode? Let's work through this problem together. We'll start by listing what we know. Since we're told the pH is 9, the hydrogen ion concentration is 10 to the power of minus 9 molar. The equation for the hydrogen electrode is H plus 1 electron makes 1/2 hydrogen gas. We'll assume that the pressure of hydrogen is held at 1 atmosphere. From the equation, we see that 1 electron is involved, so N equals 1. By convention, the standard potential is 0 volts. Now we can substitute this information into the Nernst equation. From the equation for the hydrogen electrode, we see that Q equals H2 over H plus. By evaluating the equation, we find that the electrode potential is minus 0.531 volts. Let's start our discussion with the example of a Daniell cell. As a Daniell cell starts functioning, the concentration of copper-2 ions starts decreasing, and that of zinc ions starts increasing. It means that Q, the reaction quotient in the Nernst equation, is increasing. This shows that the cell voltage will decrease. At one stage, the concentrations of both the ions become equal. This indicates that the reaction will reach equilibrium and the voltmeter will read 0. For this situation, the Nernst equation can be written as shown here. However, at equilibrium constant Kc is equal to concentration of zinc 2 ions over the concentration of copper 2 ions. Substituting the values of R and F and of T as 298 Kelvin, we get the equation for equilibrium constant Kc as shown here. Consider a galvanic cell made from half cells using magnesium and nickel. Notice that the ion concentrations are all 1 molar. What is the equilibrium constant of this cell? Try to solve this problem on your own before proceeding. Let's start with the half reactions to find E cell. Since nickel has the greater reduction potential, it is the cathode and magnesium is the anode. By substituting the standard reduction potential values as shown in the equation here, you can find that E cell is 2.11 volt. You can rearrange the equation that relates E cell to the equilibrium constant to solve for the log of Kc. You should memorize this equation. You can then substitute your information about this cell into the rearranged equation. Log of Kc is equal to 71.5. To find Kc, you can take the inverse log or the exponential function of both the sides. This gives us a value of 3.16 into 10 to the power 71 for Kc, an extremely large number. It is also possible to derive an equation relating the Gibbs free energy and the cell potential. The equation is shown here. This is another equation that you should memorize. Note that standard cell potential is an intensive property, but the Gibbs free energy is an extensive property. The value of delta G depends on the number of electrons transferred. You already know that the Gibbs free energy is related to the equilibrium constant by the expression delta G is equal to minus RTLNK. With these equations, you can easily calculate the equilibrium constant and the Gibbs free energy for a given electrochemical cell. Let's consider a galvanic cell at 298 Kelvin. This cell is made from half cells containing aluminium and zinc, where the ion concentrations are 1 molar. From the table of standard reduction potentials, you can easily find that the standard cell potential at these conditions is plus 0.90 volt. We first need to look at the balanced equation. Since zinc has the higher electrode potential, zinc undergoes reduction, while aluminium undergoes oxidation. Notice that 6 electrons are transferred in the equation. 6 electrons are lost to oxidize 2 aluminium atoms to aluminium ions. Therefore, N is equal to 6. You know that delta G is equal to negative NFE cell. You can substitute these values in the equation. We get the Gibbs free energy is equal to negative 521 kilojoules. You can find Kc from E cell. Start with the equation relating E cell and Kc. Rearrange to find log of Kc and substitute. Log of Kc is equal to 91.525. So, we end up with a Kc value of 3.350 into 10 to the power 91. With the galvanic cell, the cell potential is always positive. It means that the Gibbs free energy for a galvanic cell is negative, which is consistent with a spontaneous process. A spontaneous process favors products. So, we see large values of the equilibrium constant. There are some key terms that you must first understand before proceeding to study the conductance of electricity. The first key term is electrical resistance, which has been given the symbol R. It is the opposition to the passage of an electric current. Resistance is measured in ohms. The SI base units for ohm are kilograms meter squared per second cubed into amperes squared. The electrical resistance of any object is directly proportional to its length, L, and inversely proportional to its cross-sectional area, A. We need a proportionality constant to turn this proportionality into equality. This proportionality constant is called resistivity or specific resistance and is represented by the Greek letter ρ. The SI unit for resistivity is ohm meter. Quite often, its submultiple, ohm centimeter, is also used. Remember that 1 ohm meter is equal to 100 ohm centimeters, or 1 ohm centimeter is equal to 0.01 ohm meters. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then resistance R becomes equal to the resistivity ρ. Thus, resistivity is defined as the resistance of a substance when it is 1 meter long and has a cross-sectional area of 1 square meter. Conductance, which has the symbol G, is the inverse of resistance. Thus, we can write that G is equal to 1 upon R. Since R is equal to ρ into length upon cross-sectional area, we can say that conductance is equal to area divided by ρ into length. The unit for conductance is the Siemens, which has been given the symbol S. Siemens is equal to ohm inverse or mho. The reciprocal of resistivity is known as conductivity. Conductivity is represented by the lowercase Greek letter kappa. Thus, we can write that kappa is equal to 1 upon ρ. We can substitute kappa in the equation we wrote a little while ago for conductance. Now we can write that G, conductance, is equal to kappa into cross-sectional area upon length. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then conductance becomes equal to kappa. Thus, conductivity is defined as the conductance of a material when it is 1 meter long and has a cross-sectional area of 1 square meter. The SI unit for conductivity is Siemens per meter. Sometimes this is given as Siemens per centimeter. Note that 1 Siemens per centimeter is equal to 100 Siemens per meter. The magnitude of conductivity varies greatly as shown in the table. It depends primarily on the nature of the material, although temperature and pressure can also affect conductivity. Depending on the magnitude of their conductivity, materials are classified into conductors, insulators, and semiconductors. Conductors are materials with large conductivities, such as metals and metal alloys. Some non-metals, including graphite, carbon black, and some organic polymers, also act as conductors. Insulators are materials with very low conductivity, such as glass and ceramics. Semiconductors have conductivities between conductors and insulators. These important electronic materials include silicon, doped silicon, and gallium arsenide. Apart from the three materials discussed, there are other special types of conductors known as superconductors. Superconductors have zero resistivity or infinite conductivity. The earliest materials identified as superconductors were metals and alloys at low temperatures, below 15 Kelvin. Certain ceramics and mixed oxides show superconductivity at temperatures as high as 150 Kelvin. Now let's discuss about the conductivity in metals, that is, metallic conductance. Metallic conductance, or electronic conductance, is the electrical conductance through metals. As the name indicates, the conductance is due to the flow of electrons in the metal. Metallic conductance depends on the nature and structure of the metal, the number of valence electrons per atom, and the temperature of the sample. Now, let's move on to the conductance in electrolytic solutions. You know that pure water exhibits conductivity, although it is very low. The concentration of hydrogen ions and hydroxyl ions in pure water is 10 to the power of -7 molar. Due to the presence of these ions in very low concentrations, pure water has a very low conductivity. When electrolytes are dissolved in water, ions are released into the solution. As the ions go into the solution, its conductivity increases. The conductance of electricity by ions present in a solution is called electrolytic conductance or ionic conductance. The conductivity of aqueous solutions depends on several factors, including the nature of the electrolyte, the size of the resulting ions, the solvation of the ions, the concentration of the electrolyte, and temperature. Directly measuring the conductivity of ionic solutions is problematic. Passing a direct current into an ionic solution changes the composition of the solution, as electrochemical reactions may occur. Also, unlike a solid conductor, such as a metal wire, we can't connect a solution to a Wheatstone bridge. To measure the conductivity of an ionic solution, we use a conductivity cell, like the one shown in the illustration here. A conductivity cell contains 2 platinum electrodes coated with platinum black, separated by a distance, L, with a cross-sectional area, A. An alternating current source is used as the source of power. The column of the solution separating the 2 electrodes then has a resistance described by the equation R is equal to rho into L upon A. The cell constant, G star, depends on the distance between the electrodes and their cross-sectional areas. G star is equal to L divided by A. The unit of cell constant is per centimeter. If we know the length and the area, we can calculate the cell constant directly. However, direct measurement of the length and area of cross-section of the electrodes are both difficult and unreliable. A better approach is to determine the cell constant by measuring the resistance of the cell when it contains a solution of known conductivity. For this purpose, we use potassium chloride solutions whose conductivity is known accurately at various concentrations and temperatures. The table here shows the conductivity of different concentrations of potassium chloride solution at 298 Kelvin. The cell constant, G star, is equal to resistance into conductivity of the solution. Once we know the cell constant, we can use it to measure the resistance or conductivity of any solution. To measure the conductivity, we can use a Wheatstone bridge. This device contains 2 resistances, labeled R3 and R4, and a variable resistance R1. The conductivity cell is the unknown resistance R2. The Wheatstone bridge is connected to an AC power supply and a suitable detector. When the bridge is balanced, no current flows through the detector. At these conditions, R2 is equal to R1 into R4 divided by R3. Inexpensive conductivity meters are commercially available and can also be used to measure the conductance or resistance of the solution in a cell. Once the cell constant and solution resistance are known, we can calculate the conductivity of the solution by dividing the cell constant by the resistance. The conductivity of different electrolytes in the same solvent and at a given temperature varies. This is because of variations in the charges and sizes of the resulting ions, the ion concentrations, and the ease of ion movement in the presence of a potential gradient. Therefore, we introduce the concept of molar conductivity, which uses a Greek letter lambda with a subscript m as its symbol. Molar conductivity is related to solution conductivity by the equation lambda m is equal to kappa, or conductivity divided by concentration of the solution. If concentration is expressed in moles per cubic meter and conductivity in Siemens per meter, then the unit for molar conductivity can be written as Siemens meter square per mole. To use molarity, which is a far more common concentration unit for chemists, we need to convert the units, resulting in the second equation given here. Let's work through a typical problem together. A conductivity cell is filled with 0.1 m KCl. The resistance of the KCl solution is 200 ohm. The same conductivity cell is filled with 0.03 m NaCl, and the cell resistance is 500 ohm. What is the conductivity and molar conductivity of 0.03 m NaCl? The conductivity of 0.1 m KCl solution is 1.29 Siemens per meter. Note that there are multiple parts to the problem. Here's our strategy. First, we need to find the cell constant, G star. We can do this by using the information given about the KCl solution. We know that G star is equal to conductivity multiplied by resistance. Given that the conductivity of a 0.1 molar potassium chloride solution is 1.29 Siemens per meter. Remember that Siemens is equal to inverse ohms. The resistance of the solution is measured to be 200 ohms. Therefore, the cell constant is the product of 1.29 times 200. The unit of ohms cancels, giving a cell constant of 258 inverse meters or 2.58 inverse centimeters. With the cell constant, we can now find the conductivity of the 0.03 molar sodium chloride solution. We know that conductivity is equal to the cell constant divided by the resistance of the solution, which has been given as 500 ohms. So, we calculate that the conductivity of the 0.03 molar NaCl solution is 0.516 Siemens per meter. We can use the equation shown here to find the molar conductivity from the conductivity and the molarity of the sodium chloride solution. By substituting and evaluating, we determine the molar conductivity to be 1.72 into 10 to the power 4 Siemens meters squared per mole. The conductivity and molar conductivity of an electrolyte change with the concentration of the electrolyte. As concentration decreases, conductivity decreases for both strong and weak electrolytes. This is because there are fewer ions per unit volume to carry current as the solution is diluted. However, molar conductivity increases as concentration decreases. The variation is different for strong electrolytes and weak electrolytes. Before we discuss the concentration dependence of molar conductivity, we must first understand the idea of limiting molar conductivity. This is the conductivity of a solution as its electrolyte concentration approaches zero. Limiting molar conductivity is given the symbol lambda m naught. The molar conductivity of strong electrolytes is weakly dependent on concentration. If we plot a graph of molar conductivity against the square root of concentration, we see that the y-intercept is the limiting molar concentration. The slope of the resulting line is the Kohlrausch coefficient, which depends on the specific salt. The Kohlrausch coefficient depends on the cation and anion charges of the ions formed by the electrolyte. You can classify electrolytes by the charges formed. For example, NaCl is considered to be a 1,1 electrolyte, since the sodium ion is +1 and the chloride ion is -1. Using similar reasoning, you can classify calcium chloride as a 2,1 electrolyte. Magnesium sulfate is a 2,2 electrolyte. All electrolytes of a particular type have the same Kohlrausch coefficient. Kohlrausch carried out studies on limiting molar conductivity for a variety of electrolytes. From his work, he deduced the law of independent migration of ions, or Kohlrausch's law. This law states that limiting molar conductivity can be represented as the sum of the individual contribution of the anions and cations of the electrolyte. For a salt of general form AYBZ at infinite dilution, limiting molar conductivity is equal to Y times the limiting molar conductivity of cation A plus Z times the limiting molar conductivity of anion B. Try to work through this problem on your own before checking the answer. Calculate the limiting molar conductivity for sodium sulfate from the data given here. Sodium sulfate contains 2 sodium ions and 1 sulfate ion. From Kohlrausch's law, the limiting molar conductivity is equal to 2 times the limiting molar conductivity of sodium ions plus the limiting molar conductivity of the sulfate ions. Substituting the values from the table, we get the limiting molar conductivity of sodium sulfate as 260.2 Siemens, centimeter square per mole. The molar conductivity of a weak electrolyte depends greatly on the concentration of the solution. This is because weak electrolytes have a low degree of dissociation as concentration increases. Since the relationship isn't linear, we can't determine the limiting molar conductivity by extrapolating back to zero concentration. At infinite dilution, the electrolyte dissociates completely, but the conductivity is so low that it can't be measured directly. Instead, we can use Kohlrausch's law to find the limiting molar concentration. We can approximate the degree of dissociation, alpha, for a weak electrolyte as the ratio of molar conductivity to limiting molar conductivity. If the molar conductivity and the limiting molar conductivity known, then the dissociation constants for weak electrolytes at a given concentration can be found. Here is a typical problem. The conductivity of a weak acid in solution with a concentration of 0.002034 molar is 5.67 into 10 to the power -5 Siemens per centimeter. Calculate its dissociation constant if the limiting molar conductivity is 452 Siemens centimeter square per mole. Try to solve this problem on your own before checking the solution. First, find the molar conductivity using the equation you learned earlier. On substituting the values, we get the molar conductivity as 27.88 Siemens centimeter square per mole. Now, you can find the degree of dissociation for this weak acid, since you know that alpha, the degree of dissociation, is the ratio of molar conductivity and limiting molar conductivity. By substituting the values and simplifying, we get the degree of dissociation as 0.06168. With the value of the degree of dissociation in hand, we can use the equation relating Ka and alpha. Substituting the values, we get Ka is equal to 8.25 into 10 to the power minus 6. An electrolytic cell is an arrangement in which an external source of voltage brings about a chemical change. Since electrical energy is put in, the reaction is non-spontaneous. When you recharge a battery, you are actually running them as electrolytic cells. Let's look at a simple electrolytic cell. As shown in the diagram here, it consists of 2 copper electrodes immersed in an aqueous copper sulfate solution. The electrodes are connected to a DC power supply. When the power supply is turned on, reduction occurs at the cathode, which is the electrode connected to the negative lead of the power supply. Oxidation occurs at the anode, which is connected to the positive lead of the power supply. The reduction half reaction at the cathode has copper 2 ions gaining 2 electrons to form metallic copper. At the anode, copper metal undergoes oxidation by losing 2 electrons to form copper 2 ions. Students often find it difficult to remember the difference between galvanic and electrolytic cells. In galvanic cells, the anode is considered to be the negative electrode, and reactions are spontaneous. The cell potential is always positive, and the change in Gibbs free energy is negative. In electrolytic cells, the cathode is considered to be the negative electrode, and the reactions are non-spontaneous. The cell potential is negative, and the change in Gibbs free energy is positive. Remember, in any cell, oxidation occurs at the anode and reduction occurs at the cathode. For example, an impure sample of copper can be used as the anode. As the cell runs, pure copper is deposited on the cathode. Less reactive metals, such as silver and gold, and non-reactive impurities fall to the bottom as anode sludge. Similar processes are used to produce sodium, magnesium, aluminium, and other metals on large scales. Michael Faraday was the first scientist to quantitatively study electrolysis. Faraday's work can be summarized in his 2 laws of electrolysis. Faraday's first law states that the extent of chemical reaction that occurs at any electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. The electrolyte may be molten or in an aqueous solution. In other words, the mass of an element that deposits at an electrode during electrolysis is proportional to Q, the total amount of electricity passed through the cell. Faraday's second law states that the amounts of different substances produced by the same amount of electricity passing through the electrolytic solution are proportional to their equivalent masses. Equivalent mass can be calculated by dividing the atomic mass of a metal by the number of electrons needed to reduce a cation. The amount of charge Q passed through the cell can be determined from the product of current and time. To determine the charge in coulombs, multiply the current in amperes by the number of seconds for which it was applied. The stoichiometry of the half reaction needs to be considered in quantitative electrolysis. The half reaction relates the number of electrons to the metal deposited. For example, in the reduction of silver ions, 1 mole of electrons is needed for each mole of silver ions that reduce. You know that the charge on one electron is equal to 1.6021 multiplied by 10 raised to the power of minus 19 coulomb. Hence, the charge on 1 mole of electron is equal to the product of the charge on an electron and the Avogadro number. This can be written as the product of 1.6021 multiplied by 10 raised to the power of minus 19 and 6.02 multiplied by 10 raised to the power of 23. Therefore, the charge on 1 mole of electrons is equal to 96,487 coulombs per mole. This quantity of electricity is called Faraday, which is symbolized by capital F. Sometimes, this is rounded off to 96,500 coulombs per mole of electrons. Now use all this information you just learned to solve a problem. A 2.50 ampere current is passed through molten magnesium chloride for 15.0 minutes. What is the mass of magnesium deposited at the cathode? Let's work through this problem together. First, we'll find the charge that passed through the cell. You know that charge in coulombs is equal to the current in amperes multiplied by the time in seconds. We need to convert 15.0 minutes into seconds. 15 minutes into 60 seconds per minute is equal to 900 seconds. The current is 2.50 amperes. The charge that passed through the cell is then 900 seconds times 2.50 amperes, which is equal to 2,250 coulombs. From the half reaction, we see that 2 moles of electrons are needed for each mole of magnesium atoms that form. Therefore, we require 2 Faradays, or 2 multiplied by 96,487 coulombs, to deposit 1 mole, or 24 grams of magnesium. Therefore, for 2,250 coulombs, the mass of magnesium deposited is equal to 24 grams per mole multiplied by 2,250 coulombs divided by 2 multiplied by 96,487. Thus, 0.2798 grams of magnesium is deposited at the cathode. The products of electrolysis depend on the nature of the electrolyte being electrolyzed and the type of electrodes used. Inert electrodes do not participate in the chemical reaction. Inert electrodes act as a source or a sink for the electrons, providing a surface for the electron transfer. Platinum, gold, or graphite electrodes are commonly used as inert electrodes. On the other hand, active electrodes do participate in the chemical reaction. Active electrodes are used in the electrolytic refining of metals, which we discussed earlier. Thus, we can conclude that the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis reactions depend on the oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Some electrochemical processes are kinetically very slow. At lower voltages, these processes don't seem to occur at all. In order to make these processes occur, extra potential, called overpotential, must be applied. For example, the electrolytic decomposition of molten sodium chloride will produce sodium metal and chlorine gas. In this case, only one cation, that is, the sodium ion, and one anion, that is, the chloride ion, are produced. Sodium ions are reduced to sodium metal at the cathode, while chloride ions are oxidized to chlorine gas at the anode. The electrolytic decomposition of aqueous sodium chloride solution, on the other hand, produces sodium hydroxide, chlorine gas, and hydrogen gas. In this case, besides sodium and chloride ions, hydrogen ions and hydroxide ions, along with water molecules, are present. Let's look at this process in detail. At the cathode, either sodium ions or hydrogen ions may be reduced. As the hydrogen ion has a higher standard electrode potential than sodium, it gets reduced. However, hydrogen ions are produced by the dissociation of water. Hence, the net reaction at the cathode may be written as the sum of these two reactions. Thus, we have the reduction of water as per the equation shown here. At the anode, too, there are two substances that can be oxidized: chloride ions and water molecules. At first glance, it would seem easier for water to get oxidized than chloride ions, since the electrode potential of water is lower than that of chloride ions. However, the oxidation of water is a kinetically slow process. Hence, an extra potential called overpotential is needed for the production of oxygen. This explains why chlorine, but not oxygen, is produced during the electrolysis of aqueous sodium chloride. The net reactions of electrolysis of an aqueous solution of sodium chloride are as shown here. It is more challenging to predict the products of electrolysis reactions in aqueous solutions. Due to overvoltages, you can't rely solely on standard reduction potentials. Reduction will occur at the cathode, but there are two possibilities for the reduction half reaction. First, ask yourself if the cation is a transition metal or a representative metal cation. Transition metal cations will undergo reduction, since they have favorable reduction potentials. Representative metal cations will be too difficult to reduce. Instead, water will be reduced at the cathode, forming hydrogen gas. Predicting the oxidation half reactions is more complicated. It depends on the relative ease with which the different species present in the solution are oxidized. Halide ions will undergo oxidation to form the diatomic elements in preference to water. However, chloride ions undergo oxidation in preference to water due to overvoltage of oxygen. On the other hand, oxoanions are too difficult to oxidize. So, water is oxidized to form oxygen gas. The ability of a cation to be reduced or an anion to be oxidized not only depends on their standard reduction potentials, but also on their concentrations. Hence, to account for the effects of concentration, the standard electrode potentials are replaced by the electrode potentials given by the Nernst equation. In dilute solutions of sulfuric acid, water will be oxidized to release oxygen gas. However, in concentrated solutions of sulfuric acid, the formation of the peroxydisulfate ion is favored. Let's test our knowledge by solving some practice problems. Try to answer this question on your own before proceeding. Predict the products and write a balanced equation if an aqueous solution of silver nitrate is electrolyzed. Assume that the electrodes are inert. Let's start with the reduction process at the cathode. Silver, a transition metal, has a favorable reduction potential. So, silver ions will be reduced to form silver metal. The half reaction is written out. Since the electrode potential value of water is less than that of the nitrate ion, water will undergo oxidation to form oxygen gas as shown in the half reaction. Now, we can sum the two half reactions. We need to make sure that the number of electrons gained is equal to the number of electrons lost, and then add the half reactions to write the overall equation. Here's another problem. Try to answer it on your own first. A dilute solution of sodium sulfate is electrolyzed. Predict the products of the electrolysis, assuming that the electrodes are inert. We'll use the same basic strategy as the previous problem. At the cathode, it is easier to reduce water than the sodium ion, as it has a higher standard reduction potential value than sodium. So, water will undergo reduction to form hydrogen gas. At the anode, it is easier to oxidize water than the sulfate ion, since the standard reduction potential for water is less than that of sulfate ions. Water will oxidize to produce oxygen gas. We need to make sure that the number of electrons gained is equal to the number of electrons lost. By summing the two half reactions, we can write an overall equation. Note that H plus OH minus make H2O. If you have ever observed rusted iron, tarnished silver, or the green patina that develops on copper or bronze, then you are familiar with corrosion. Corrosion is the term used to describe the process of the surface of metal objects getting covered by oxides or other salts of the metal. In corrosion, the metal is oxidized by losing electrons to oxygen, forming oxides. Corrosion is essentially an electrochemical process. Let's look at the corrosion of iron, which is commonly known as rusting, in detail. Iron corrodes in the presence of water and air. The spot where the corrosion begins can be considered the anode. Here, iron loses 2 electrons to form the iron 2 ion. The oxidation half reaction has an oxidation potential of minus 0.44 volt. The electrons thus released then move to another spot on the metal, which then behaves as the cathode. At this spot, oxygen is reduced in the presence of a hydrogen ion to form water. The hydrogen ions are believed to be available either from carbonic acid that is formed when carbon dioxide dissolves in water, or due to the dissolution of other acidic oxides from the atmosphere. The reduction potential for this process is 1.23 volts. In the overall equation, iron is oxidized to iron 2 ions, while oxygen is reduced to form water. The cell potential is 1.67 volts, consistent with a spontaneous reaction. The ferrous ions formed are then further oxidized by atmospheric oxygen to ferric ions in the form of hydrated iron 3 oxide, commonly known as rust. It is very important to prevent corrosion because it damages electrical towers, bridges, buildings, which can collapse as a result, and ships, which can develop a breach. Corrosion can also force major industrial plants, such as power plants or chemical processing plants, to be shut down. Hence, corrosion not only results in loss of money, but also endangers public safety. How can corrosion be prevented? One way is to cover the surface with paint or some chemicals like bisphenol. This creates a physical barrier that protects the metal. A second alternative is to cover the surface with other metals, such as tin or zinc. Like paint, this prevents oxygen and water from reaching the metal surface. We can also use electrochemistry to prevent corrosion. In cathodic protection, the metal is coated with another metal that is more easily oxidized. In cathodic protection of iron, iron becomes the cathode and the metal coating becomes the sacrificial anode. Cathodic protection can be used to protect steel pipes from corrosion. Magnesium oxidizes more readily than iron, as you know from the table of standard reduction potentials. In this diagram, a magnesium rod is buried and soldered to a steel pipe. Magnesium acts as the anode and the pipe acts as the cathode. The damp soil acts as an electrolyte. The magnesium rod can be dug up and replaced. This is much faster and less expensive than replacing the pipe itself. Try to answer this question on your own before proceeding. Based on the table of standard reduction potentials, which of these metals could provide cathodic protection to iron? Aluminium, copper, nickel, or zinc? Answer: aluminium and zinc could be used to protect iron from corrosion. As shown in the table, their reduction potentials are more negative than that of iron. This means that they are more readily oxidized than iron. Copper and nickel reduce more readily than iron, making them unsuitable for cathodic protection.